All right. I know you're very excited to do this, so we should start and get going. I can see you're so happy about this. All right, so look, linear algebra. It's not a very exciting sounding thing, but it turns out to be an incredibly important, integral part of all sorts of scientific enterprises. And I know a few of you here, in all sorts of different kind of capacities. Maybe you're here to get through this course. Unfortunately, you ended up in linear algebra in some way. Many of you may be here because it's essential to what you do. Can you hear me okay? All right? Okay. Anyway, it's awesome, right? So it's really great. That's the surprise. It turns out to be a very fantastic, enjoyable thing. And it has a very nice, well-connected kind of story that we're going to go through, right? So there's going to be these, unfortunately, I think something like 26 lectures. It's a bit longer. The fall semester is a bit longer than the spring one, right? So I'll show you. I'm going to have slides today for a lot of the day, but most of the time it's going to be on the blackboard, right? That's what we're going to do. There will be also MATLAB this time round, so I'm sorry about that for some of you, but Matrix Laboratory, right? It was built for that. So it's essentially you work on something like that as well, so you can kind of get your hands dirty. But really what I want you to be able to do is pencil and paper stuff, right? I really want you to understand it. We're going to prove everything as we go through. My name is up on that thing, I guess. Let's see. Maybe, yeah. So I'm Professor Dodds. I'm in math and stats, but I'm kind of a hybrid character. I come from theoretical physics and math and electrical engineering. So I have that kind of background. But I spent 6 years in the social sciences at Columbia. So I have this kind of very mixed set of interests. And maybe I'll talk about some of the stuff we do in our work. I'm the director of the Complex Systems Center here at UVM. You can come and check out some of the stuff we do. Together with my colleague, Professor Danforth, we run the Computational Story Lab, which is awesome. And we have a great bunch of kids in that. So some of you may be interested in joining that later on, one day, eventually. All right. So as I said, I'm going to give you some slides to kind of warm things up. Let's see if this works. Okay. And I'm sorry, this is a complicated room, right? So I can turn off the lights, but you'll go to sleep. You're going to go to sleep anyway. Should I make it really easy? I would like to switch off the lights, but I'm afraid that if I press these buttons, ugh. Does that help? That's not bad. Okay. All right, I can't see what's going on, so I'll just pretend. All right, so I like to draw little doodles, so you'll get a few of those throughout the course. So some orientation. There is a website for the course. I'm just going to yell. I'm going to yell. I like yelling. So there's a website for the course. I'm calling it Matrixology, by the way, because linear algebra is a terrible term. It's awful. It's embarrassing. Calculus, for whatever reason, it's a great sell. People are like, oh, my 12-year-old daughter appears last night. She says, I want to learn calculus. And I say, well, let's start with some algebra. But she knows there's this magical, and then she says, well, what is it? No one knows what calculus is, but it's magical, right? You should know it. Linear algebra is just, okay. So I'm going to try and orient you as to how those things go together and why linear algebra is much better. All right, so there's a website. There is even, this is actually important. Let's see if it works. Oh, because UVM, nice. Come on. Web connection. Who would want a web connection? Yeah. Okay, so there are tweets. There's a Twitter account, Matrixology Vox. So I have 3 courses that I teach regularly. Principles of Complex Systems, which has Pux Vox. I'm kind of excited about that. And there's a Networks Vox as well, Complex Networks. So they're a pair, they're graduate level kind of things. So Matrixology Vox, so the voice of Matrixology. So I'll tweet from this. I will occasionally send you awful things through email, because email is still something that people use. Occasionally I'll be forced to do that, but I would prefer to do this. And you should tweet at this thing in polite, nice ways and ask questions to this account. The human at the other end, which apparently is me, will try to put things up. So I also put up a lot of videos So one thing I'd like to do is we go through, because I haven't taught this course since 2011, as you'll see. This is the 8th season, actually. Anyway, so I call these seasons, episodes. They're all these little silly things I do. I'll put up videos, right? This is how we do it, okay? It's a little explanation things, a little helpy things as we go along. So office hours, which we have to sort out when they'll be, but if you can come to those, you can give me ideas like what's going wrong. I'll go and record a little video, put it up, tweet it. Boom. Okay? Cool? Exciting, right? YouTube. So I'm a fan of YouTube. See, lots of fun. There's going to be fun things, right? It's going to be fun things. The T-shirt there says, well, you can get to that. I updated that. Okay, anyway, all right. So fun things. Yeah, so we're going to call them episodes. The lectures are episodes. So for instance, today, these are the lectures. You can go home and print out, kill some trees. Be happy, go kill some trees. You can print out the lecture slides from today, and I make them in these different flavors. So there's a version which you can print out like this and write on. Most of the time, it's going to be, as I said, on the board. I'm going to call assignments levels, just for fun, like a game. So we're going to have levels. We're going to have 10 levels that you have to level up through. The way the grading works is it's 0 if you've just made a total mess, like, for instance, left the question unanswered. 3 if it's all right, or if it's almost all right, the nuclear reactor's not going to explode. 2 if it's sort of more like a revision thing. So 2 if you need some revisions, 1 if you need major revisions, right? So it's a better scoring system at both sides, right? So you'll be able to see that, generally speaking, people are like, okay, this is really a 2 out of a 3, and I can judge that. In fact, we have graders. We have a Department of Truth. Actually, we have a Department of Truth. So there'll be some secret grader people who will be doing that for you. Of course, you can complain, but generally speaking, this works much better. It's better than having a question out of 17 or something, which I used to do and made a mess of. All right. Challenge levels, which are sometimes called exams or midterms, so we're going to have 3 of those. There is a whole bunch of homework here. If you're really psyched about this, I know one person in the history of this course has done this, has gone through all of these. These are extra things you can work on for no credit whatsoever, right? Just because you love it. So, you can dive into those. These are just recommended extra ones. There are 2 versions of it. There is a textbook. So there are 2 versions of this textbook. And I give you edition 4 and edition 3. They're all listed. So that's for the, if you're heroically excited. There's a couple of papers you can look at, all sorts of things. All right. Oh, even nice things that students said about me. Obviously, I left out all of the bad things. These are just nice things. All right. So you can feel like you're in a good place. I did not make them up. Should have. Okay. Never thought of that. All right. So let's see. So, okay. So there's a website. You should come to the website. You should follow the Twitter account. You should tweet. Maybe that's illegal for me to tell you to do that. But you should tweet. Tweeting is fun. But politely. Okay. So, right. Let's go through. Let's go through some slides here. I'm going to orient you with this whole linear algebra business. What I really prefer to call Matrixology. There's actually going to be a split, and I'll sort of have some story. I don't know why I'm wandering around this thing, but it's here. We're going to have a sort of a split. There's going to be a fork in linear algebra. There's going to be there's sort of a pure version for people who want to go into abstract algebra and do all the pure math stuff, the secret things, right, that no one can explain, those things. That's where you have to go. And then there's going to be our version, right? There's Danforth and me teach this version. It's going to be called applied linear algebra, which is somewhat insulting. But we have a different focus. We have a different focus, and I'll try to explain what that is today. And this is the MIT version of linear algebra. So I did my PhD there. Gil Strang, who I'll mention, was an advisor, faculty advisor, and he is, you can look him up. He has videos online because of the open courseware, so you can look at those as well. When I fail you miserably, you can go and look at those. They are really just videos. They are just videos. Of him at a board. Anyway, he's a very famous character. He's won all sorts of national awards and things for his linear algebra course and other kinds of teaching. He does all sorts of things. So he is a person to look up. Let's see. Anyway, that's the flavor. That's the flavor. It will not be quite the entire course that gets rammed down people's throats there. So you should feel like you'll be happier people. All right, so we have admin kind of things, which I've talked a little bit about. I want to give you some motivation for this whole Matrixology thing, why it's important, right? I mean, we could go on forever about this. I will tweet about it, so you can enjoy those things. some places where it's used, and it's used everywhere, and there's a good reason for that. And some really fundamental problems that we're going to tackle, right? So as I said, there really is kind of a narrative to this particular course. There is one simple little equation, right? And it's basically this thing kind of on drugs, right? 2x equals 4. You can all deal with that one, I'm sure, right? So we're going to be essentially just doing that in a crazy way. And it takes us in lots of different directions, but that will be the big story. All right. Okay. There's a Colbert. Colbert, who's no longer with us, apparently. Disappeared with Santa Claus, so he's gone. But there's a little video of his. All right. What else? Yeah. And today I will frame this story. There are 3 ways of looking at this equation, the matrix version. And the matrix version is going to be this. It's so dark, isn't it? I'll turn off the lights. Ax equals b. That's what it's going to be. This is a font notation here, right? A's, matrices. We'll talk about what these things are, but matrices, they're numbers in boxes. Matrices, I will have this little double line on them, because this is what I do, so you'll know what they are. Vectors will have these little hats on them, right? Yeah, so, and I draw, just so you know, I have the little cursive, these things going on. B, C, these are all matrices, right? I haven't used chalk for a while. Good, all right? Okay, so there's the style, all right. All right, we're in the right place. As I said, there's a course website. There is this textbook, which of course is available for like $10, right? I don't know, some awful amount of money, I'm sure. But you can buy it, you don't have to buy it. I can't force you to buy it. I will give you everything you need, pretty much. But if you're really pumped and psyched, you should get it, right? And you can get the 3rd or the 4th edition. Presumably the 3rd edition is cheaper. All right, so here they are. All right, very funny. So the 2 on the left are the ones you want. Either, as I said, would be good. There's a link. So all these slides, by the way, if you get these slides up on your browser and things don't explode, you can click on these things. You can download the PDFs you link on these things. They'll take you there, and hopefully those things still exist. Let's talk about why we're doing this. So I had this little, was a little fracture between pure and applied math. We are the filthy applied mathematicians, really, physicists. So here's a quote from, this is actually on Amazon. This is George Cobb, who's a professor at Mount Holyoke, or was at the time. Do you want a book written by a mathematician with a lifetime experience using linear algebra to understand important, authentic, applied problems of former president of Siam, which Strang was? Or do you want a book shaped mainly by the aesthetics of pure mathematicians, with only a weak theoretical connection to how linear algebra is used in the natural and social sciences? So, boom. I feel I have to do that because we get the abuse from the pure mathematicians who feel we are the low people. But I care about reality. That's my interest. All right. Okay, so there's Strang, so it's MIT. We get a little geeky. We make this is a birthday of his, and there are 11 by 11 matrix. It's 121 cupcakes with numbers, all right. So it's pretty bad. But he's a good guy. He was a Rhodes Scholar back in the day, good fella. And actually, I have to add this. It's not always true. It's rarely true. Really nice person. It's not always true. All right, so Strang, you can look him up on Wikipedia. All right, so a bit of a champion. That's a Laplacian matrix. So, in many ways, we are just kind of getting to the end of this, and we'll be able to say, oh, x equals 2. We'll be doing the matrix version of that. Well, it'll take a whole course to do that, which doesn't seem terrific, but that's what we're doing. All right, so there's an outline. Again, if you want to print this out, you can. That's available on the website. Just gives you the syllabus, various things, how to behave. The couple of papers you might want to look at, they're short, too much calculus. You say, I'm going to have a little dig at calculus just for fun, everyone's a good person. The fundamental theorem of linear algebra is what you are getting to by the end of this course as well. So that's something you could read at the end, which sort of has everything tied together. But this is a bit of this short piece, the too much calculus, is that you get lined up with 50 million flavors of calculus, and the world is, there's a lot of stuff that's discrete, and often we make it discrete. And that's when linear algebra often comes in. It's not just there, but okay. So office hours. So I'm over in Farrell Hall on the Trinity campus, the Triangle building at the back, on the 2nd floor. So we'll figure out times, like I'm thinking maybe Monday, Tuesday, and Wednesday we'll have an hour or something on each of those days. But I'll sort that out, possibly through tweets. This died. What did die? Death of thing. Why dead? All right. Bad behavior. Okay, so I said they're going to be these levels, which are really assignments. They're going to have 8 basic questions, 8 pencil and paper questions, right? On each one. And then there'll be a couple of MATLAB questions, which some of you will not find the greatest thing in the world. I will try to give you help online again with YouTube. That is a new piece that we've been adding. And what did I do? I lost my thing. All right. I could. Okay, all right. Here it is. All right. Singularly dead. It's just dead. You died on me. Bad thing. Why did you die on me? All right. All right. Okay. All right. So there are 10 assignments. 10 assignments. The last one can't be dropped, which sounds ridiculous, but this is some sort of game thing I'm giving you. But it can't be dropped because it's a synthesis of, you need to have used everything that you've learned so far to be able to do it. So it isn't one of these courses where you get through the first 4 weeks, you do an exam, that's gone. You'll actually, in the final exam, have to be able to do everything through the whole course, which is old school, but there you go. Challenge levels. We're going to have our exams in here, and they will be at the end, roughly, of every 4 weeks. Right? So 7 lectures, exam, 7 lectures, exam, 7 lectures, exam. And then we'll have a few more at the end before the final exam. They may drift a little bit depending on how fast I speak. The final bus level is May 4th, which is a long way away, and it might be warmer by then. All right. Okay, lots of fun. You're going to have a lot of fun doing it. This is upsetting me. Let me see. Homework, I told you about homework. Good. Turn up, come to lectures. Let me know who you are. It's nice that I know who you are. If things go badly for you, then, it's good that I know who you are. But you should come to lectures. All right, better. I told you about the scoring system. Okay, and here's our basic structure, right? So as I said, there's going to be these 4-week kind of blocks. We have the spring recess complicating things a little bit. But you can see the structure here. 4 weeks, AX equals B to start with, then what I'm going to call the big picture. I'm just going to throw it at you and see what it'll fill in. It's definitely a big puzzle kind of course. There are bits and pieces floating around. Eventually at the end, everyone will understand everything, and you'll all be really happy. That's my goal. All right. Eigen stuff. So some of you may have come across eigenvalues and eigenvectors if you've had other kinds of courses where they just appear. So we'll do that in a very nice, deep way. There's beautiful things in there. For some reason, we'll look at the Fibonacci series just for fun. Find the most irrational number, golden ratio, good stuff like that. But that's a fantastically powerful story, right? The eigenvectors and eigenvalues. Eigen means self or same from the German. So these are the natural elements or the natural directions, if you like, or the natural modes of systems. So this is an incredibly important kind of story here. All right, so we'll get to that, and we'll get to this thing which, again, it's a branding issue, right? So Newton and Leibniz, we know these people. We know Newton was a psycho, he gave up at 40 and went off to the mint and made money. We would have gone to Wall Street now, right? That's exactly what he would have done, at age 23 probably. But he was one of those people, Okay, so, and then Leibniz, who probably knew what was going on, I had this big fight. But linear algebra, yeah, I don't know. It's just some people, right? Who were those people? No one knows. They're not famous. Why are they not famous? It's a tragedy. All right, so we'll see if we can make them famous. All right, they didn't have okay. So SVD, ridiculous. But this thing is everywhere, right? Singular value decomposition, it's everywhere. And it turns out to be a great thing you can do to every rectangular matrix. All right, do you know about these things? I'm just putting them up there for you when you can escape at the last point. Don't do that. You should do this course. Access, if you need help, you can come and talk to me. I will email you, but Twitter is really the thing. Sorry, that's not there. Should be there. It's all right, so be good people. Don't tweet or text in class. Unless you tweet at the that's complicated. I do sometimes have official tweet wranglers. So if you're interested in that, you can tell me. People who want to tweet from class. So yeah, you can email me things, and of course send messages to the Twitter account. Other people can see that. So be nice people. Right. Don't be late with your assignments. We're going to hand them in at the start of the Thursday lecture, generally speaking, which means that one of them, you'll hand in your assignment, sit down and do an exam. Yay. All right, I said this thing about computing. Do you all have computer accounts? I tried to set that up. Look at you, so enthusiastic. No? Maybe? No? Okay, so I'll get that to work, right? I think Vote may be the place to go. It's sometimes called Vote, but Vote is right. Okay. Okay, you got to write these things out. That's what we're doing. There's going to be a little bit of this MATLAB stuff, and I know it's going to be a bit of a business, but for the most part, you're writing out your answers. Writing. Okay, that's what's going on. All right. Such a strange position here. All right, so what are we doing? All right, so linear algebra, discrete problems, right? Things that are broken up into little pieces. Information, right? Everywhere, all the time. This is what we're dealing with all the time. People, of course, we're these relatively discrete units. So we're a funny example of things that are discrete and continuous, right? You have blood in your veins, and they obey fluid mechanics, and fluid mechanics is calculus, right? But then calculus, you take fluid mechanics, and we discretize it because of the way we measure things. And you solve problems, and you have to use linear algebra to do that. Networks, that's a big part of my research over the last 5 million years, however old I am. Complex networks, there's been this huge explosion. So if you're interested in research and these sorts of things, it's been a very, and continues to be a very exciting time. Networks have always existed, it's just we've been able to quantify them and measure them and then start to see what the shapes are. Sounds, musical notes, right? So lots of things have discrete structure. So, and as I said, for fluids, even things that are discrete, and you may prefer LPs and actually listening to people in reality. Of course, we've gone to this whole discretizing things. Right. Lots of areas. These are just a few. I like to say this thing socio-technocene, which is where we are, not the Anthropocene. People plus computers. But lots of areas, and it's not just the so-called hard sciences, but it's often economics and sociology and all sorts of things. PageRank, right? So PageRank is fundamentally a linear algebra problem. It's one of these things that's sort of somehow sitting in there. That's really what it is. So it was this kind of a giant matrix being solved, right? Which pages point to which other page? And that was fantastically successful to start with because it's not just this raw algorithm, it's people plus computers. People made meaningful links. So I realized the other day my website, which has sort of evolved, it's nothing spectacular, but it's been around since 1995, right? It's old. People, you made meaningful links. You like cats, you make links to cats. I mean, that's what happens, right? So people would do this. So there's really meaningful human-based stuff in there. And then you have this raw algorithm that comes along and finds structure. And that was a big transition. You guys didn't exist, of course, but before that you had search engines that just went to sites, and if it said cat 1 million times, then it would say that's an important site about cats, right? And it's actually about the whole structure, which things point to which things, which point, and so on. So it's true of social phenomena, it's true of Supreme Court decisions, it's true of all sorts of things, the way citations work. If you have an important thing citing something else that's important, then that reflects on objects going out. All right. Okay, linear algebra. Okay, so I have this thing. It's the calculus is the blue pill. All right, we had this one. Too much calculus. Right, matrix. All right, matrix reference. So now, if you haven't, maybe you've probably played around with matrices at some point, but now we're going to do a whole course on it. See, sneaky. It was always there. Evil calculus. So this is the truth. So they have a serpent. We're going to have platypuses. I come from rural Australia, actually, so my grandmother once saw a platypus in the wild. They're hard to see in the wild, but they are excellent, excellent organisms. But here's some sort of more serious thing. So up the top, we have continuous phenomena, so these are waves, fluids, and then discrete pieces over here. And there's an interplay between those because sometimes when we measure things, we force them to become discrete because we're going to put it onto a computer. So suddenly it's discrete. Sometimes discrete things become continuous, which is super weird, right? But it's true of fluids. Again, fluids, right? So, and the air is full of all these little molecules, but behaves as a continuous material. We've sort of understood this thing a long time ago, that you can explain how these, all sorts of fluids, right? It's the oceans, it's the actual Earth itself, blood in our veins, move, honey, right? They all obey the same equations, the Navier-Stokes equations. It's kind of amazing. But if you look at all, if you get right down to it, they're little discrete bits that are next to each other, which is pretty weird. So you've got that going on, but when it's evidently continuous, you go off to the serpent side. Matrixology comes in when it's evidently discrete, but then sometimes you're in a continuum thing and you have to move back and forth between them. That's very exciting for you, I know. So there are these back and forths in different ways. Science is describe and explain. From there you go to create and share. So create is to engineer. So to engineer sounds good, right? It sounds good, but it doesn't, Okay. All right, so that's just sort of how those things are roughly connected. It's not everything, it's some of it. Matrices do a whole bunch of things, right? So they can be gadgets, they can transform things, right? So here we have a little vector x prime, which is resulted from a times x. So they can make vectors become other vectors, right? So it could be as simple as these sorts of things where you can stretch something or shrink them or rotate them. So, video games and movies and all those sorts of things, when you're sharing and changing things around, it's all these linear transformations, which are embedded, encoded in matrices, right? So a 3x3 matrix encodes a three-dimensional rotation. There are special ones that do. And a 2x2 matrix, just a 2x2, will encode different kinds of rotations. All right, so that's an important thing to realize about how these matrices operate. And these are really for square matrices. You can get into some deeper things as well. Powerful, right? Very powerful little objects. Pictures, right? Pictures are matrices. So this is something completely different, but they're matrices. I mean, every time you take a picture, you make a little matrix. And they're usually, the standard thing, it's RGB. It's actually 3 matrices, right? There's red, blue, and green. And ridiculously, when you put those things together, you see a beautiful colored image. This is Brutus. Brutus is about 40 years old, lives largely on the north shore of Oahu. I had a conference there because, but he just came up on the beach and went to sleep. So matrices, and that means you can start to do lots of things with them, right? So if you know how matrices behave, you can start to do things like encryption and pulling them apart, taking out the most important piece, finding which pieces are important and so on. So there's a lot of image manipulation. So here's this is SVD actually. This is the singular value decomposition thing we'll get to at the end. One of its uses is to take a matrix, and this is used for weather forecasting and all sorts of stuff to do with economics, right? You can take out the most important aspects of some giant horrible matrix and say, well, the matrix is just, here's a good version of it. Here's a rough approximation of that matrix. So what is this? So what I'm going to do is add these little corrections to it, right? So I have 60 matrices, and when they're all added together, you get the original one. But all of these matrices are actually separate from each other. So if you know anything about Fourier spectra, right, anything like that, or just think of orchestras, right? You're adding sounds together to make a symphony or an orchestra. That's the same kind of idea. And if you can go the other way around, right? So you can approach a sound, or say an orchestra again, and then break out, you can pull out the viola or the tuba or whatever it is, right? You can actually break them apart if you have the right kind of gadgetry. So I'm going to add these pieces at a time, see how quickly you can figure out what it is, right? So this is sort of, in a sense, the most important underlying mode. And we'll add one. And it's hard to tell, but that's actually what's being added, that little bit there. It's not much of it. It's sort of a correction. So what is it? So it's a face already, right? Because we have the whole face recognition system in the brain. So you can see it's a face. Yeah, so it's Einstein, right? It's just 3 of these things. And you're good, very good. All right, and that's 10, that's adding 10 of these. And what they really are like Scottish tartan, which is kind of odd. They're Scottish tartan. You're adding these kind of just rectangular looking patterns on top of each other. So the Scots, they're always good. 20, 30, there's 30. So you can see there's not going to be much more detail. So I'm going to add 30 more matrices in this next bit. And it just, if you look very closely, you'll see that it's cleaning up little details. And then you get to the original, you get to the original picture, as good as it is. All right, Einstein, another questionable character. Anyway, so these are really different things, right? So that was using matrices to move, to change images and pictures and locations and so on, to shift things around. Pictures, just pictures themselves are matrices, so it's a completely different business. And something, you know, as simple as this is fitting a best line. So you want a best line of fit. I think people do this all the time, and then start projecting about what's going to happen in the future or what did happen in the past, all sorts of things. Very standard thing to do. So linear algebra actually gives you the nicest way of doing this. If you do it in calculus, you get the least squares approach. So you're minimizing the error. So you're trying to find the line that minimizes. So you take the distance, the error, and square it for each sample, add them up, and then you want to move your line around until you get the minimum error. So that's very sensible. But there's actually a deeper kind of beautiful way to think about this in linear algebra that matches up. Right? So you know, sometimes it's better to do things in calculus, sometimes it's better to do in linear algebra, sometimes they match up. And in this case, very nice. Yeah, so this is a very controversial thing. So it turns out this is energy usage of organisms as a function of size, right? So you have little, this is just random stuff I'm telling you, but you have shrews, tiny little guys, 3 grams, talking about mammals, 3, 4 grams. Their heart rates go berserk, right? They're just ticking away, and they're very, very small. And they use, per sort of cell, they use a ton of energy. They're just running really crazily fast, right? And their clock is going really fast. But they don't use up, when you look at the whole shrew, it's not a lot. And then you scale up to elephants. And of course, if you could measure blue whales, you could do that as well. But the question is, how does that scale, right? So as you get bigger and bigger organisms, what has evolution produced, and what can evolution produce in terms of these machines, right? How efficient are they? And so the big argument for 70 years now has been whether it's 3/4 or 2/3, which is a difference of a 1/12. So people get upset about how to measure that straight line. Anyway, that's a different thing. But right, lines of best fit all over the place. Okay, it's evil. I hope you understand that. It's evil. All right, this is something we'll get to in that 3rd section that I talked about with eigen stuff. So we're going to connect these things together, which is a bit odd. Fibonacci is going to be in there. It's just going to be this tiny little matrix, very benign little character. There it is. Some 1s, a 0, hanging out, 2 by 2, it's no big deal. That's got all sorts of good stuff inside it. And Harvard Square has something to do with this as well, but I don't want to say too much about Harvard. It's not a good place. Let's see. So, yeah, all these things. Right. That's going to be fun. So as I said, it's you're going to solve problems with pencil and paper. There's going to be some of this MATLAB shenanigans as well. But it is, you know, building these techniques, and things come together eventually, right? So Karate Kid fans, no, okay. You're going to paint things for a long time, and then eventually you'll be able to win Matrixology competitions. All right. Okay. So here are some really central pieces of linear algebra, problems within linear algebra, right? I've given you examples of things, but so the first one is this AX equals B business, which I wrote on the board and you can't read. And the thing you know is A, right, and B. So you know these 2 pieces. And I'll try to, this is what we're really going to dig into in the next 6 lectures after this. So the game is you know A, you know B, what's X? So it's exactly this, 2x equals 4. And in general, we're saying we know this, we don't know this, we know this. So what this is like is saying, I want to make this musical signal, right? This is the symphony that I want. And I've got, in A, I have an oboe and a viola and all these things. I have all these notes. And I want to know how to combine them to produce this sound. You can kind of go back and forth. This is, you know, sort of a sketchy idea, but put it into your heads roughly. I mean, music very much is a linear superposition, so it works. The eigenvalue problem, which will come up in the third 4-week block, is a different game. So here we have A, which we know. We know A, and it's a square matrix. We know A, and A can be rectangular in that first case. We know A, and we want to find which vectors does it not change the direction of, right? So which vectors does it really like? This is this eigen thing, which vectors, you put them into this little machinery that's A does something to the vector in general, it wants to like move it around. There are some vectors that it just gives you, it brings the vector back. It may stretch it, it may make it point in the opposite direction. That's the eigenvalue story. And this one, which you'd get to in a differential equations course, which I can hear just, yay. Differential equations, but this is the best part of differential ODEs. This is a beautiful, beautiful thing, right? So you'll have, and these are vectors, you have derivatives of some vector, which is a function of time, is equal to some matrix times that vector. So again, it's this linear combination of things through A. Right? And I'll say these words, we'll get these words again and again and again. There's going to be a lot of repeating. So mostly it's 1. We're going to have to look at 2 because it's awesome, and it matters for 1. But you could think about the whole course about being about 1. And there are different ways to orient these courses and so on, but I think the sequence is pretty cool. Okay, so, and 2 is just, yeah, the last one is number 3. You don't have to worry about it now. All right, somehow you're going to understand this thing, this horrible mess, right? The big picture. This is the thing that I want you to understand completely. And it will take a while. We're just going to fill this in slowly, right? We're going to start with the left-hand side a little bit. Down the bottom, we're going to get this thing which we'll call null space. We'll get this thing called column space. And eventually, these other weird things will fill in. Left null space is the, let me say it like this, it's the known unknowns, right? It's the stuff that you cannot represent, right? So for whatever reason, it's the sounds your orchestra can't make. But you know they exist, but you can't make them, right? It's close to the Dunning-Kruger effect, which if you don't know about, you should look up. It's very important for humans to know about. But basically, yeah, this stuff comes to you, and you have building blocks in your head, right? And you can recognize things. I mean, think about the sounds we can hear. There's a certain spectrum, right? And same with light. There's a certain amount of stuff that we can take in and understand and comprehend and deal with, and then other things that just go straight past. And we're at a point, at least now, with, say, light and sound, that we understand the limits of people, right? So there's this kind of idea of, I'm being very rough here, but left null space, this weird thing, left null space, is the stuff you can't, it doesn't grab when it goes past. But linear algebra, we know it exists, so it's kind of okay, right? We've got a handle on it, we can quantify it, which seems weird. All right, so that's weird. Okay, and this is the thing we'll get to at the end of two of these blocks. So at the end of 8 weeks, I want you to understand this, that there'll be, in that second row, second column, I've got to get that right, there's a second column, this is sort of example types of matrices, and they will have these kind of big picture structures like this. It's okay, this is a mess, fine. This is going to fill in slowly. But I want to put it out in front because this is not a mystery whodunit thing. You should know that there's a place you're going to, right? Right, cool. Okay, so I'm going to set up a few things, and then we'll work through some examples. If I can turn the lights back on. Interesting. All right, so I've kind of said this, right? So AX equals B. B you can think of as the sound you're trying to produce. It's the reality you're trying to get to. A has the building blocks that you have at your disposal. These are the things you can engage. And then just simply add together. And X is about how they combine, right? So X is this mystery bit that you have to figure out. And so we can't always do it. All right, so this is a fun thing. I tweeted it for you from the Matrixology Vox thing. Radiolab piece. Radiolab goes up and down, but this is a kind of an extraordinary piece of a person who basically can do this linear algebra thing to an extraordinary degree, which is they can run, this guy can run 4, well, they could test more, I suppose, but they got him to run 4 symphonies in his head, starting at different times, and then at some point, 3 minutes later, he could tell you exactly where they all were. And he can visualize them, right? So he can kind of zoom in and turn them on and off and do all these sorts of things. It's bananas, right? It's just sort of, it's kind of like being able to jump 40 feet in the air. Like, it just sort of doesn't make any, it's just, to me, it doesn't make any sense. Okay, all right, other things are like this as well. Okay, this is your left null space, hilarious. So you want a tiny left null space, actually. This is something you want a very small version of, right? You want to make that really small, because that's the stuff you cannot understand. Okay, Dunning-Kruger. All right, there you go. You can be hilarious in a geeky way. So if you know X, let's say you solve one of these problems, which you get to, and we're going to do it in this abstract way. It's just what we've got to do. You can get to compressing information. You can probably land a tiny little robot on a comet. You can do those sorts of things. You can get get the whole Google thing to work. You can also do these sorts of things, right? We can start to alter information, a bit like this guy who could turn the sounds on and off, right? We can start to filter things because we know which building blocks are in there. You can find a system's most important features. Okay, here's a system, we're going to break it down. Here's the most important bit. This is the next most important bit. And they're at right angles to each other in a sense, right? Okay. So you can figure out how to play around with things. All right. Okay, so that's a sort of a broad story, right? I just, we are going to get down to, as we'll start now, pencil and paper. And you're going to be solving basic problems, right? We're not going to be doing things with symphonies, but I'm just trying to give you the picture that you should be thinking about. So there are 3 ways to think about this AX equals B problem. And it's the row, column, and matrix pictures, right? These views. And we're going to work on this little example. So here it is. Usually you'd probably see X and Y, right? So this is simultaneous equations. Use that term, you use those kind of words maybe. It's a system of linear equations. Right? They're linear, there's no x squareds, there's no y cubes, there's no exponential of something. They're linear, right? You're just adding simple things together. And we're going to use x1 and x2 instead of x and y because we're going to go x3, x4, x5, x6. We'll have up to whatever we need to. So we'll be very happy with n-dimensional space. Right? We're not going to think about what a 4-dimensional banana looks like. We're not going to do that. Don't worry, it's okay. But we're going to have arbitrary dimension. We should be happy with that. So we're going to say this is a 2-by-2 system of equations. And you can, and this is a good thing to write down. I'm going to start writing the board in a second. There are 2 equations and 2 unknowns, right? That's what's going on here. And then, the usual thing is you figure out some way to mess around with one of them and subtract it from the other one. And so you've probably done that, right? What we're going to do is create a very principled way of doing that right? So it could be, in general, 33 of these things across this way, x1 up to x33, and there might be 17 equations. 17 is a really random number, right? 17 equations. And somehow you have, that's a messy thing to deal with, right? You don't want to be saying, well, I'll add some of this. We're going to have a principled way that you and computers can cope with. And in general, if you can deal with, say, 3x3s with pencil and paper and say maybe up to 4x4 is sort of the most, 3x3s, usually you get enough complication to see the bigger story, right? And then you can tell a computer to do 100 by 100. Computer do this, right? Bad computer. Okay. And the computer will love it. It's a bad relationship. Okay. They like being punished. Okay, so let's see. So, okay. So let's do it. So this is going to be the row picture. And we understand this is 2 lines, right? These are 2 lines in this x1, x2 space that they're hitting each other. And we're trying to find where if there's a solution. So that's going to be a story that we'll start with. Then we'll get to the column picture. Okay. I'm going to try and turn on a light, which I feel is hard. Oh, gosh. Okay. All right, let's write this down. And I like using colored chalk. I'll get some colored chalk. I brought in some giant sidewalk chalk, but I stopped because You can't erase it, I realize that. Okay. So let's have a go at this thing. Okay, good. It's exciting. All right, it's so exciting. Okay. I mean, the really good things, everything will work out. You know, you just load it into your heads, everything will work out in a nice way. Okay, so we've got this example, and we'll start to identify some shapes here. So I'm sure you could figure this out. This is a plus 2x1 plus x2 equals 4. So I'm going to start by doing this and say this is rho. This is going to be notation. This is r equals rho. Right? So we'll build up a principled way. We could do this in kind of a messy way to start with, but let's start doing the right way straight away. So, for instance, you could just say, let's subtract the second equation from the first equation. That's going to get rid of this x2 here. So that feels good. That feels like we did a good thing. But I'm going to say, no, you want to actually get rid of this one first. So when we get to 100 by 100, we're going to have a really systematic way of doing it. So this is a systematic way. Right? Systematic approach. We're going to start with, and there's row 1, row 2. We're going to get rid of this one here first. So the next thing we write down is row 1 doesn't change. And then we're going to write a new row 2. And this is an important little bit of notation over here, so we know what we're doing. Row 2 over here. We're going to say row 2 is equal to the old row 2. And this is always, we're always going to do this. This 1 is here. There's a 1 here. Right? Always do this. Yes, you could say 3 times row 2 or 4 times row 2. You could do something like that. No, bad. Okay? Always. So it's always there. And then we're always going to subtract something. This is where I need colors. We're always going to subtract something times row 1. So this is all here. And then this part is what changes. And if you think, well, let's think about this. We want to get rid of this 2x1. So to get rid of this 2x1 using the first equation, what's the kind of obvious thing to do, right? You mumble at it. You multiply by 2. Yep. So you can multiply by 2 and just add it, right? Fine. But we're not going to add. We're going to be a little silly. We're going to take this number 2, and then here is a minus 1. That's a minus 1 thing, right? So this is 2 minus 1. So this is from the 2x1 in row 2, that part. And this one is from minus 1 times x1 in row 1. So let's see what this did. It ends up as being plus 2. Now, why does that always work? Whatever number this was, right? This could be 36, and this is 17. So if we multiply the first row by 36 and divide it by 17, and then subtract it from the second row, we're always doing the right thing, right? We're changing what's in front of this guy to be 2, and then subtracting it, right? We multiply by minus 2, this becomes a plus 2. So we're trying to make what's here the same as this one. All right, so it's simultaneous equations, but we've got a real structure for how we're doing it. All right, row 1 doesn't change. This is the new row 2. See if you can write down what the new row 2 is. Horrible thing to ask. I'm so sorry. Is the volume still good? People at the back? I want to ask about the content. Linear algebra will make you very happy. I promise it. It's not a cult. It's not a cult. You have to do the work. This is not a hazing process. Okay, so, right, we're going to add, so it ends up being adding 2 of this. Add 2 times this guy. So that's going to make this 0 times x1. Good. That's a good thing. We're going to 2 of this. What do we get here? We get, 3x2 equals 6. So this is our new row 2 prime. And we could simplify that a little bit because it's looking pretty good. So let's simplify that. Let's make one more step. Equals 1. This is still row 1. I want to identify. So this is, let me write this as well. This is a row operation. So I'll try to introduce these words as we go along. Spectacular words. It's a row operation, right? We used a row to do something to another row. Row operations. All right, so we could simplify this. This guy's gone, and we could make this x2 equals 2. And this is row 2 double prime is equal to row 2 prime multiplied by 3, a third. So this is pretty good. We know what x2 is now. Done. So we can plug x2 back into here. I know this is a tiny little example. It's a tiny little example. It's very cute. We can plug it back into here, and then we get x1. And we're going to call this step, these are the row operations go down. Back substitution is the thing that cleans it up. All right? So we now have x2 equals 2, and then sub into row 1, which didn't change. And in general, that's true. Row 1 is never, it couldn't, there's one way it could change. But in row 1 will not change as we do these row operations, even if we have 100 by 100 or 100 by 32. Excitement for you. All right. We're going to substitute into there. So we've got minus x1, and now it's going to be plus 2. Did I get that right? Equals 1. x1, we'll subtract this off, equals 1. So in calculus, you'd write this as probably like this, maybe. 1, 2, maybe? That kind of notation. Is that a good notation? Yeah? Yeah? All right, so we're not going to do that because, you know, the snake thing. And, I mean, snakes are poisonous, people. I mean, I have a dread fear of snakes. The Australia bit. It's really terrifying. x1, x2 equals 1, 2. We're going to put them in a little box. We'll put them in boxes because we're all about numbers in boxes. That's what we do in this course. Numbers in boxes. So this is a vector, which is a very, right? It's a very nice version of a matrix, right? We'll call this a 2 by 1 matrix. And I'm going to repeat myself a lot. So this is 2 rows, 1 column. And so we could actually call it something else. It is a column vector because of its columness. Awesome. It's pretty awesome. So what happened? Interesting thing happened, right? So we had this, let's draw a picture. So we always draw a picture. It's always good to draw a picture. The problem is if you have 100 by 100 or 37 by 73, also good random numbers, 33, right? How do you draw those things? That's horrible. Pretty bad. So if we had x1 plus something times x2 plus something times x3 equals 7, right? We have 3 variables. What's that an equation of? Anyone know what that is? We'll come back to this. But if I have something times x plus something times y plus something times z equals 4, or z, what's a plane, right? So it's a plane. So we can draw a plane, kind of. It's getting a little sketchy. And then we can have another plane hitting it. So they hit along a line, and then maybe another plane. But in 4 dimensions, it's a hyperplane, right? And in 17, it's bad. Drawing becomes hard. But we're going to draw pictures for these little guys. And then we'll see how the column picture allows us to think about these much higher dimensional ones. So what's going to happen is the row picture, which we're doing now, is how you solve it. The column picture is how you think about it. That's the music, that's the bits of music that are being played together to make the symphony. Cool. Okay, let's draw a picture. Okay. Or where I grew up, picture. Let's see. So let's start with our equation. So we have, well, let's see if you can do that. Draw those 2 lines. x1, x2. I'm going to indicate a few things. 3, 4. Draw those 2 lines. That we started with, right? What we're talking about is When do these two lines intersect? If they intersect. Where does that happen? So nutritious. It's great. All right. Let me see. So what's this first one? So x, so you think about it in different ways. Of course, they're all on this side, right? You could, if you want, put x2 equals 1 plus x1. That might make you feel better, right? That's a y equals 1 plus x kind of thing. All right, so we could do it like that. We can think of it like that, or we could just get the intercepts. So when x1 is 0, then x2 is 1, and when x2 is 0, x1 is minus 1. So it's this guy, right? Right, so this is our first equation, which we're kind of calling row 1. There we go. The second one, when x1 is 0, x2 is 4. So it hits here. And we go through here as well, because when x2 is 0, x1 is 2. Right, so we've got this one here. Oop. Wow, bad drawing. Okay. If I draw it in straight lines, this is what it should look like, right? So this is where they hit, and that was our solution. This is x1, x2 equals 1, 2. Yes? This thing down here, that should be a minus 2, you're right. Yep. Yep. Brain issues. Sorry. It's a chalk. Yeah. Okay. Right? Right? So we can kind of look at this and we can see it. But as I said, as we go up to higher dimensions, trouble. But what has happened actually as we've changed these equations? Well, let's look at this one here. What's this? So we've actually we've changed the system. This is a different system, but it has the same solution. So that's what's happened. So row operations. So this is important. Everything is important. Row operations change the system to simpler ones, right? To increasingly simpler ones. Let's write it like that. I'm making this up. Increasingly simpler ones with the same solutions. With the same, can you read this? It's the same solutions. So let's draw this one down here, right? So this, I've labeled them, I think, so I should label this one as well. This is minus 2x1 plus x2 equals 4, and this is what we called row 2. So down here, we have the same equation for row 1. So let's draw that one. So it looks like this. Minus 1, 1. Very exciting. Row 1. So we have minus x1 plus x2 equals 1. This is row 1. Right, so what's this guy? x2 equals 2. What's that thing? Yeah, straight line goes across here. Whoop. This is x2 equals 2, and this is row 2, well, we double prime. We modified it twice. So, same solution. 1, 2. So, we could have gone one step further, actually, right? We could have, say, taken this equation and subtracted off here and gotten rid of that x2. And if we'd done that, and we will do that in another treatment, then this line would have gone to here. So row equations do this. They actually do a funny thing, right? They take lines that are pointing in funny ways, or planes or hyperplanes that are pointing in funny ways relative to the underlying Cartesian axes, right? Thank you, Descartes. And then make them match up parallel, and then the solution just falls out. Right? So it's important to see that you could have gone one step further. We could have done that. All right. Okay. I think that's pretty good. Yeah. So let's see. Can I turn this off? I know it's a little crazy. Would should be able to read it. So what we're doing with this row picture, right? We're finding an intersection of two lines. Easy peasy, right? And we want to know when those the values of x1 and x2 went for which both of those equations are true, right? And they're only true at one point. So geometry and algebra is very nice, right? We can just do the algebra. We tell the computer to do algebra. It doesn't need to think about lines or planes or anything. It just does the thing, right? But it's very nice for us. And here's a point that, let me just, okay, good. So here are three things here that could happen, right? So they could be that the lines intersect at one point, and this is just this 2x2 example. They could be parallel to each other, or they could be on top of each other. And they give you the three possible solutions for AX equals B in general, right? This whole AX equals B business, you can either have one solution, one unique special solution, zero solutions, or infinitely many. 0, 1, and infinity. That's basically all the numbers you need. They're really good. Good numbers. And it's written out here, right? So if they intersect at one point, we have one solution. They're parallel, there are no solutions. And if they're the same, infinitely many. Okay, good. So is that kind of okay? It's just, yeah, we're just warming it up. Excitement is building, I know. All right, let's look at the, but I've touched on this, how this is going to be bad when we go to 7x17s and things. We don't. It's going to be hard. It's going to be hard, right? Because you're starting to think of I don't know, hyperplanes in 33 dimensions. Like 17 of those guys intersecting each other. It's just your brain can't do it. Right? Let me draw. I got to turn the light. Let me draw the three possible solutions here. Three possible outcomes for these sort of simple, for this kind of case, is parallel, so no solutions. One solution, just to draw them pictorially, because they're not up there like that. And then they're actually on top of each other. Infinitely many solutions. Same lines. Which seems like a weird thing and shouldn't happen, but it does actually. The way it can happen is you have a big system, you start to do some of these row operations, and then you end up with things that match up. All right. Coolness? I think it's cool. Okay, good. Okay, let's, so it will be on the board, going forward, but let's, today there's going to be just some messing around. All right. Okay, the column picture. Okay, so we've got the same story here, same equations. So we're taking this tiny little example, and then we're going to blow it up. We can write it in this way. So have a look at this, and you should write it down. And we'll draw a picture of it. What we're doing is we're saying, well, we could write it in this kind of addition of vectors version. So there's a 1 and a 4 on the end. We're going to stack them and make a vector out of them. And we're going to take the prefactors, right? There's a -1 and a 2. We're going to make that a vector. And a 1, 1, they're attached to the x2s. And we're going to make that a vector. We're going to write the whole thing out like this. So those two, so the first one is just two lines of equations. Now we've got a nicer picture, actually, because we're just writing actually one line. It's one line now. Right? There's just one x1, there's one x2, and there are these vectors, these three vectors. So this becomes this general problem. It's x1 times some vector plus x2 times some vector equals b. And the column picture is exactly this idea of a1 is the viola, a2 is the tuba, and you want some amount of both of those beloved instruments to add together to give you b. I'm sure Brahms wrote duets for the two instruments. So column vectors are our building blocks. They're the things you have in your head that you know about. These are the things you can see. Right? They're the good things. And we're trying to reach B. We're trying to create B out of A1 and A2. We're trying to make those two things. All right, so let's do the column picture here. We're using the same story, column picture. Now, if you haven't seen matrices before, this is going to be a bit funny, I suppose, to start with, but we will keep explaining how these things work. I will keep explaining how these things work. In the third lecture, we'll do a lot more about matrix multiplication. This is sort of just to get things out in front of you. Okay, so we're going to transform this problem into x1 times minus 1, and it's a 2, plus x2, 1, 1, equals 1, 4. Now, the important thing about this is the x's are now just these kind of variables. We're no longer in what I would call x1, x2 space. Right? These vectors live in some other space. These guys live in y space. We'll call this y space. This will keep, this notation will keep, right? X's and y's. We'll keep that the whole way through. So let's draw a picture of how this works. And I need to label this. This is going to be our vector A1. This is our vector A2. And this is B. Little a's, we're going to get bigger. The big A is going to be made out of these guys when we get to it. All right. Okay. So let's draw these two. So A1 and A2. So A2 is here. Right? 1, 1. This is going to be A2. And A1 is here. It goes this way. Minus 1 in this direction. And then 2. So that's A2. Good. And we're actually in a different set of axes. I'm going to label them y1 and y2. Right, x now, the x1 and x2, these are stretchy things, right? They multiply these base vectors. Right, here's the sound of the viola, here's the sound of the tuba, and we're going to dial them up or down depending on x. And we know, and we're trying to get to this. We're trying to get to B, which is here. It's 1, 2, 3, 4. So B is actually here. B. We're trying to make this B. And it works like this. This is 2 times A2. This is 1 times A1. Sorry. I labeled these the wrong way. This is A2. This is an A1. A1, A1. A1. A2. A2. Oh. A2. Fatiguing. All right. So this guy in here, it's this vector. It's 1 times A1. Right? Addition of vectors. And this is 2 times A2. This guy here. So you could say 2 times A2 plus A1, or A1 plus 2 times A2. And we get to B. Right? So B is equal to 1 times A1 plus 2 times A2. So this is our solution in here. This is the solution we got in that first place. Equals 1, 2. Now, we didn't find, so important, we didn't get the solution in this column picture version, right? We didn't get 1, 2. I'm just using it here. We see how it works well. We use the row picture to get the solution. The row picture is not illuminating. This is much better, and you can see how this is going to work in higher dimensions. You're actually just trying to add up a bunch of vectors by stretching them, shrinking them, maybe multiplying some by 0, just getting rid of them, and then you're trying to make some resultant vector, trying to make B. So that's an easier thing, may not be, but that's an easier thing conceptually, right? That's a better thing conceptually. And it maps onto exactly this story that I'm trying to tell about music, for example, just as one kind of example. So that's the column picture. You can see where the column picture will go wrong. So column picture possibilities. So you can have this kind of thing. Here's B, A1, and A2. And you can see there is some way of multiplying A2 and some way of multiplying A1 to get a solution. So this is one solution. The fact there's one solution may not be completely obvious. If this is A1 and this is A2 and this is B, they're both pointing in the same direction. You've got two violas and you're trying to make a viola plus a tuba, you can't do it. Right? So no solutions. So these are the things that map back to the row picture. The row picture had a different, the row picture in this case was two parallel lines. Here it's two parallel base vectors. And infinitely many solutions looks like this: A1, A2, and then B. So you have two tubers, and you're trying to make a tuba. Tuba. So there you can say, oh, I want a little bit of this one, or a lot of that one, or a lot of this one, a little one. So this turns out to have infinitely many solutions. So that's the three ways of seeing it in the column picture. All right. So I did 2 times A2 here, and that's a 1. That should be that's a 1. Yeah. Sorry. Font issues. Sorry. It would be good to make sure that one. So this is where the Europeans actually have some, they kind of get out in front of just a couple of places, not many, but 7 is good. That's a good thing, and they have the 1 going on. Okay. My problem. All right, thank you. So, but that's right. Yeah, that's good. Yeah. Okay, so the last picture, and so we can do this, we'll finish it up, is the matrix picture. So we love the column picture. These are things you'll have. It's intuitive, maybe not yet, but it will be. And you can think about it in many, many higher dimensions. And just keep going, no problem. Which is, in higher dimensions in this case, you've got a whole orchestra, right? That's a higher dimensional thing. We're not thinking about, 5-dimensional space. That hurts. That's very bad for us. We're not allowed to do that. Our brains just can't do that very well. But we can think about adding lots of things together. That's fine. And I've just drawn pictures of what these are, right? So if A1 and A2 are pointing in, they're not parallel, then you have one solution. If they're parallel but not parallel to B, then there are no solutions. And if they're all parallel to each other, infinitely many. Assuming, you don't have any zeros. Okay, so one thing is, if there are no solutions, do we give up? Of course we don't give up. We're on a heroic journey. We find the X that gets you as close as possible, right? So you make the sound that's as close as possible to the goal sound, right? Which kind of explains people on American Idol. So this is a method of approximation. It's incredibly important. That line of best fit, that's exactly what it's doing, right? You've only got 2 choices. You've got the y-intercept and a slope, and you've got a bazillion other things, so you're going to make a lot of mistakes. That's fine. So we do that a lot, actually. So there's a method of approximation that we'll come to. It'll take a while to get there. So we don't have the best building blocks, but we get as close as we can to our goal. All right, so the matrix picture, let's just say what it is. We can combine this column picture structure. We can put those A1 and A2 things together and make a 2-by-2 matrix. And if you know about matrix multiplication, which we're going to get to, you can see that it's really A times X equals B. And now we're in this situation where we have a matrix A, which does things. It's a -1, 1, 2, 1. It's a matrix. When it multiplies a vector, it does something to it. Twists it, turns it, something. We have to figure out how that works. It takes a while to get to it, but it transforms it. There's rotation is one thing that a matrix can do. It can flip it, just flip the whole thing. And you very much think of how you might play around with pictures on a digital manipulation, right? You can flip the image this way, you can rotate it, you can stretch it in this direction and stretch it in a different direction this way, right? So that's exactly what happens. But it can be not at all obvious which directions that matrix likes, right? It might like to stretch in this kind of odd direction. All right. Okay, so I think we'll finish now. I'll be able to finish. So a couple of last pieces are this. One of the big things we'll do throughout this course is decomposition or factorization of matrices, right? So you have this matrix, and it could be a square matrix, it could be a rectangular matrix, some big nasty looking thing, and it turns out that rewriting them into a product of 2 much simpler matrices or 3 much simpler matrices is a very natural game, right? That's something that has been just understood for a long, long time, and there are different ways to do it. They don't have very good names, actually, right? So there's LU decomposition. L for lower, U for upper. These are not well done. AX equals B. We say X equals B all the time, or a system of linear equations. We're not marketing this very well, but these are the words. QR decomposition, A equals U sigma VT. This is this SVD decomposition, and this beautiful one at the end is eigenvalue decomposition. All right, so we're on our way. You may run away, and you'll get your first assignment on Thursday. Questions?